This is the second video in the series where we show that given a right-angled triangle where edges A and B are adjacent to the right angle, and edge C, also known as the hypotenuse, which is the longest edge, is opposite the right angle, the statement by Pythagoras that a squared plus b squared equals c squared must be true. Simply put, if you square the sides adjacent to the right angle and add them up, that value is equal to the square of the hypotenuse. This proof is going to be simpler than the previous one, and I've linked the previous proof in the description and comments section in case you wanted to see that. Now let's give a quick explanation of the two angles that are not the right angle, the two coloured angles that are adjacent to the hypotenuse of the triangle. We know the sum of angles in a triangle is 180 degrees, and the right angle is 90 degrees, which means the sum of the remaining angles must be 90, so that everything adds up to 180. So the orange and blue angles add up to 90 degrees. And we'll make a note of that because it will be useful to us later on in the proof. Now what I'm going to do is to take 4 copies of the triangle and arrange them in a specific way. I'm going to set things up so that adjacent triangles are rotated by 90 degrees, and so that the blue corner of one triangle makes contact with the orange corner of the adjacent triangle. Let's see how this looks. I'll start with a copy of this triangle but in the same orientation. I'll add a second triangle but rotated at 90 degrees. As you can see, the triangles are adjacent and the blue corner of one triangle is touching the orange corner of the adjacent triangle. I'm going to add a new triangle adjacent to the top triangle and rotated at 90 degrees again. And we'll add one more copy rotated at 90 degrees again and adjacent to the one we just added. And you should be able to see now that for all adjacent triangles, the orange corner is making contact with the blue corner. So in all cases, the orange and blue corners are adjacent. Hopefully you can see that we've created a quadrilateral, and it's rectangular because each of the 4 angles is 90 degrees. And I'm going to show you that this is actually a square by using what we already know about the lengths of the edges in the original triangle. Note that the height of the triangle is A and the base is B. If you look at the quadrilateral's edges, take the top edge of the quadrilateral, the left part of it is a triangle height A and the right part of it is a triangle base B. The same goes for the left edge of the quadrilateral. The length of the bottom part is a triangle's height A and the length of the top part is a triangle base B. Since this is rectangular, the opposite edges have the same total length. So the length of all edges must be A plus B. Therefore the quadrilateral is a square. The area must be A plus B squared. But within the square there's another quadrilateral. It's easy to see what the edge lengths of this quadrilateral are because all of them are opposite the right angles in the triangles. So these edges must be the hypotenuse, which is C. We can figure out what the angles in this quadrilateral are by noticing that each angle in the quadrilateral is sandwiched between a blue and an orange angle. But we saw earlier that the sum of blue and orange angles is 90 degrees. The blue, orange and inner quadrilateral angles sit on a straight line, so the sum of the 3 angles must be 180 degrees. The value of the missing angle must be 180 minus blue and orange, which is 180 minus 90. So this angle's value must be 90 degrees. Each of the inner quadrilateral angles are in exactly the same situation, so all of them are 90 degrees, which makes this a square with sides C, so its area must be C squared. Earlier we saw that we were able to give the area of the large square in terms of A and B, which are 2 edges of the right angled triangle. The area was A plus B squared. But now we can give the same area in terms of A, B and C. The expression will look different, but it will be the same as A plus B squared. The large square is now made up of 5 shapes, 4 of the original triangles and an inner quadrilateral that has the area of C squared. So the area of the large quadrilateral must be the sum of 4 triangles and C squared. The height and base of the triangle is A and B, so the area of one triangle must be half A times B. But there are 4 triangles, so the area for 4 triangles must be 4 over 2AB, and that is equal to 2AB. The area of the inner quadrilateral is c squared, so the entire area of the large quadrilateral must be c squared plus 2ab. And that must be equal to the other expression that we found for that area, which is a plus b squared. And that leaves us that a squared plus b squared is equal to c squared plus 2ab. Now, if we want the value of c squared, we simply have to subtract 2ab from both sides. The plus 2ab and the minus 2ab cancel on the right hand side, and the left hand side becomes a plus b squared minus 2ab, and that is equal to c squared. Now, if we simplify this equation by expanding the brackets and performing cancellation, we will see exactly why Pythagoras was right. Hopefully you know that a plus b squared expanded is equal to a squared plus 2ab plus b squared. The left hand side of the equation has a minus 2ab added to it, so that's minus 2ab, and all of that is equal to c squared. On the left hand side, the plus 2ab and minus 2ab cancel, leaving us a squared plus b squared, and on the right hand side we have c squared, and there we have it. A squared plus b squared is equal to c squared, exactly as Pythagoras stated. You can find the alternative proof I did linked in the description. That's it for now. Thanks for watching.